Picture this: a telescope so advanced it captures images of the universe so vast, so detailed, that even the largest screens in existence, cinema domes, planetariums, entire observatories, would crumble under the weight of their sheer scale. The Roman Space Telescope isn't just another tool for peering into the cosmos, it's a paradigm shift. While Hubble and JWST have revolutionized our view of space, Roman will unveil a new kind of cosmic portrait, stitching together light from the earliest galaxies with a resolution so sharp it could detect the faintest whispers of dark energy. Imagine a single image containing thousands of galaxies, each one a universe unto itself, compressed into a dataset so massive it would take hours to download. This isn't just about seeing farther, it's about seeing differently, unlocking secrets hidden in the fabric of spacetime that even the most powerful telescopes before it could never grasp. What if the universe's next great revelation isn't just about what we see, but how we understand what we've always seen? The Roman Space Telescope will reveal the universe in a way the James Webb Space Telescope and Hubble cannot, thanks to its ability to capture images so vast that no screen in existence can fully display them. This is not a technical limitation of the telescope itself, but a direct result of its design and the scale of the data it will gather. While Hubble and JWST have revolutionized our understanding of the cosmos by capturing stunning, high-resolution images of distant galaxies and celestial objects, Roman's approach is fundamentally different. It is built to survey vast swaths of the sky at once, collecting data on an unprecedented scale. This capability will allow scientists to study the universe in ways that were previously impossible, from mapping the invisible forces shaping cosmic expansion to uncovering the secrets of exoplanets. But how does a telescope achieve such an extraordinary feat? And why does this matter for our understanding of the universe? Let's explore. At the heart of Roman's unique power is its field of view, a measure of how much of the sky it can observe at any given moment. Hubble, for example, has a field of view roughly the size of a grain of sand held at arm's length. Its narrow focus allows it to capture incredibly detailed images of individual objects, like the intricate structures of distant galaxies or the atmospheres of exoplanets. However, this narrow view means Hubble can only study a tiny fraction of the sky at a time. JWST, while even more powerful in its ability to peer into the infrared spectrum, shares a similar limitation. Its mirror, though larger than Hubble's, is optimized for extreme precision rather than wide area coverage. Roman, by contrast, is designed with a much broader field of view, comparable to the size of a dinner plate held at arm's length. This allows it to capture vast regions of the sky in a single exposure, gathering data on millions of stars, galaxies, and other celestial phenomena simultaneously. The significance of this difference lies in the sheer volume of data Roman will collect. While Hubble and JWST are like powerful microscopes, zooming in on specific targets to study their details, Roman functions more like a wide-angle camera, capturing the broader context of the universe. This approach is critical for certain scientific goals. For instance, one of Roman's primary missions is to study dark energy, the mysterious force driving the accelerated expansion of the universe. To do this, scientists need to measure how the distribution of galaxies has changed over time. By observing large areas of the sky, Roman can track the positions and movements of millions of galaxies across vast cosmic distances. This will provide a detailed map of the universe's structure, helping researchers determine the nature of dark energy with greater precision than ever before. Hubble and JWST, with their narrower fields, would require years of observations to gather comparable data, making Roman's efficiency a game-changer. Another key area where Roman will excel is in the study of exoplanets, planets orbiting stars outside our solar system. While Hubble and JWST have already made groundbreaking discoveries in this field, such as identifying atmospheric compositions of distant worlds, Roman's wide field of view will allow it to detect thousands of exoplanets in a single survey. This is particularly important for understanding the prevalence of Earth-like planets in the galaxy. By capturing large swaths of the sky, Roman can identify potential targets for further study, such as planets that might host life. Additionally, Roman's ability to observe multiple exoplanets simultaneously will enable scientists to compare their properties, shedding light on the diversity of planetary systems and the conditions necessary for life. The reason Roman's images are so large and why no screen can display them fully is tied to the way it processes and stores data. The telescope will capture images with an unprecedented level of detail, but the sheer scale of the data means that even the most advanced screens cannot show all of it at once. This is not a limitation of the technology itself, but a reflection of the vastness of the information being collected. For example, a single image from Roman might contain data equivalent to thousands of Hubble images, requiring specialized software and storage solutions to manage. This scale of data also means that Roman's findings will be analyzed using cutting-edge computational techniques, allowing scientists to extract insights that would be impossible with smaller datasets. Beyond its technical capabilities, Roman's approach represents a shift in how we explore the cosmos. Hubble and JWST have been instrumental in answering fundamental questions about the universe's origins and structure, but they were designed for targeted, high-resolution studies. Roman, on the other hand, is built for discovery. Its wide field of view will enable scientists to identify new phenomena, such as previously unknown galaxies, rare celestial events, or unexpected patterns in the distribution of matter. This capability is crucial for advancing our understanding of the universe, as many of the most significant discoveries in astronomy have come from unexpected observations. For instance, the discovery of dark energy itself was made through observations of distant supernovae, a finding that required a broad survey of the sky. The implications of Roman's capabilities extend beyond astronomy. By studying the large-scale structure of the universe, scientists can gain insights into the fundamental forces that govern cosmic evolution. This includes understanding how gravity, dark matter, and dark energy interact to shape the universe's expansion. Additionally, Roman's ability to observe exoplanets will contribute to the search for life beyond Earth, helping to determine whether our solar system is unique or part of a larger pattern of habitable worlds. These studies are not just academic, they have profound implications for our place in the cosmos and the potential for life elsewhere. Of course, Roman's mission is not without challenges. The sheer volume of data it will generate requires advanced processing techniques and collaboration across scientific disciplines. Scientists will need to develop new algorithms to analyze the information efficiently, ensuring that the data is used to its full potential. Moreover, the telescope's design must balance its wide field of view with the precision needed to capture detailed observations. This has led to innovations in mirror technology and sensor design, ensuring that Roman can achieve both broad coverage and high resolution. In the end, the Roman Space Telescope's most remarkable achievement is not just the size of its images, but the way it redefines our ability to explore the universe. By capturing vast areas of the sky in a single observation, it opens new avenues for discovery, from unraveling the mysteries of dark energy to finding new worlds beyond our solar system. While Hubble and JWST have already transformed our understanding of the cosmos, Roman's approach ensures that the next era of space exploration will be defined by scale, scope, and the potential for unexpected breakthroughs. As we look to the future, the Roman Space Telescope stands as a testament to humanity's enduring curiosity and our relentless drive to uncover the secrets of the universe. The Roman Space Telescope's ability to capture images so vast they defy the limits of current display technology is not a coincidence, it is the result of a deliberate, methodical approach by scientists and engineers who have spent decades refining the tools and techniques needed to peer deeper into the cosmos. To understand how this mission has reached this point, we must follow the path of discovery that led to its design. It begins with a fundamental challenge: how do you capture images of the universe that are not only incredibly detailed but also cover such an immense area of the sky? This is where the Roman Space Telescope's unique instrumentation comes into play. At its core, the telescope is equipped with a revolutionary instrument called the Wide Field Instrument, or WFI, which is designed to capture light from vast swaths of space in a way that no previous telescope has achieved. The WFI's design is a direct response to the limitations of earlier observatories like the Hubble Space Telescope, which, while incredibly powerful, has a narrow field of view. This means Hubble can only capture a small portion of the sky at any given time, requiring astronomers to take multiple images to build a complete picture of a distant region. The Roman Space Telescope, however, is built to overcome this limitation. Its WFI is engineered to gather light from an area of the sky that is hundreds of times larger than what Hubble can capture in a single shot. This is made possible by the telescope's massive primary mirror, which is significantly larger than Hubble's, allowing it to collect more light and thus detect fainter objects. But the true breakthrough lies in the WFI's sensor technology. Unlike the charge-coupled devices, CCDs, used in Hubble's cameras, which are highly sensitive but limited in their field of view. The WFI employs a cutting-edge array of sensors known as the wide field camera. These sensors are packed with over 1.2 billion pixels, a number that dwarfs the pixel counts of even the most advanced ground-based telescopes. This high-resolution array allows the Roman Space Telescope to capture images with unprecedented clarity while simultaneously covering a vast area of the sky. The combination of these two factors, superior light-gathering power and an ultra-wide field of view, creates a unique capability that no other telescope has achieved. But how did scientists arrive at this design? The answer lies in a long history of astronomical research and technological innovation. For decades, astronomers have sought to balance the competing demands of resolution and field of view. High-resolution imaging requires a narrow field of view, while wide-field imaging sacrifices detail for coverage. The Roman Space Telescope's design represents a breakthrough in this trade-off, thanks to advances in sensor technology and materials science. The development of the WFI began in the early 2010s, when NASA and its partners began exploring the feasibility of a new space telescope that could complement existing observatories like Hubble and the James Webb Space Telescope. The goal was to create an instrument that could survey large areas of the sky quickly, enabling astronomers to study the distribution of dark matter, the formation of galaxies, and the evolution of the universe on a scale never before possible. This required not only a new telescope but also a new approach to data collection and analysis. One of the key innovations was the use of a wide-field camera, which was inspired by the design of ground-based telescopes but adapted for space. The WFI's sensors are arranged in a way that allows them to capture light from a much broader area of the sky while maintaining high resolution. This was a significant engineering challenge, as the sensors had to be both incredibly sensitive and capable of handling the vast amounts of data generated by their wide field of view. To test these designs, scientists conducted extensive simulations and prototype testing. These simulations involved modeling the behavior of light as it traveled through the telescope's optics and interacted with the sensors. By doing so, they could predict how the telescope would perform in real-world conditions and refine its design accordingly. The prototypes were also subjected to rigorous testing in controlled environments to ensure they could withstand the extreme conditions of space, such as temperature fluctuations and radiation exposure. This process of design, simulation, and testing took years of collaboration between NASA, industry partners, and academic institutions. It was a complex and iterative process, with each iteration bringing the team closer to a viable design. The culmination of this effort was the selection of the Roman Space Telescope as a key mission in NASA's science program. The telescope's development was also influenced by the lessons learned from previous missions, such as the Hubble Space Telescope and the James Webb Space Telescope. While Hubble's narrow field of view was a limitation, it also allowed for incredibly detailed imaging of specific targets. The James Webb Space Telescope, on the other hand, is designed for high-resolution imaging of distant galaxies and exoplanets, but its field of view is still relatively small. The Roman Space Telescope's design represents a middle ground, combining the strengths of these two instruments while addressing their limitations. This balance was achieved through a combination of advanced optics, sensor technology, and computational methods. For example, the telescope's primary mirror is designed to be both lightweight and durable, allowing it to capture light from distant objects without degrading over time. The mirror's shape is also optimized to minimize optical aberrations, ensuring that the images captured are as sharp and clear as possible. Additionally, the telescope's onboard computing systems are designed to process and store vast amounts of data efficiently, enabling scientists to analyze the images quickly and accurately. The timeline of the Roman Space Telescope's development is a testament to the patience and perseverance required to bring such a complex mission to fruition. The concept for the telescope was first proposed in the early 2010s, and it underwent several rounds of design and refinement before being officially selected for development in the late 2010s. The construction of the telescope itself began in the mid-2020s, with the primary mirror and other critical components being assembled in specialized facilities. Throughout this process, scientists and engineers worked closely with international partners to ensure that the telescope met the highest standards of performance and reliability. The launch of the Roman Space Telescope is scheduled for the early 2030s, marking the beginning of a new era in astronomical observation. Once in orbit, the telescope will begin its mission of capturing images of the universe that are so vast they cannot be fully displayed on any existing screen. This is not just a technological achievement, it is a scientific milestone that will allow astronomers to study the universe in ways previously thought impossible. The process of confirming the Roman Space Telescope's capabilities involved more than just engineering and design. It also required a deep understanding of the scientific questions that the telescope was intended to address. For example, one of the primary goals of the mission is to study the distribution of dark matter in the universe. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, its presence can be inferred through its gravitational effects on visible matter. The Roman Space Telescope's wide field of view allows it to capture large areas of the sky in a single image, making it ideal for mapping the distribution of dark matter across vast regions of space. To confirm this capability, scientists conducted extensive simulations and observational studies using existing telescopes. These studies involved comparing the data collected by the Roman Space Telescope with data from other observatories to ensure that the telescope's instruments were functioning as intended. The results of these studies were promising, demonstrating that the telescope could indeed capture images of such vast scale while maintaining the necessary resolution to study distant objects. Another key aspect of confirming the telescope's capabilities was the development of advanced data processing techniques. The sheer volume of data generated by the Roman Space Telescope's sensors requires sophisticated algorithms to analyze and interpret. Scientists worked closely with computer scientists and data analysts to develop these algorithms, ensuring that they could handle the massive datasets efficiently. This collaboration between different scientific disciplines was crucial in ensuring that the telescope's potential was fully realized. The confirmation of the Roman Space Telescope's capabilities is also tied to the broader context of space exploration and scientific discovery. The telescope's design was influenced by the need to address some of the most pressing questions in astronomy, such as the nature of dark energy, the formation of galaxies, and the search for exoplanets. By providing a new tool for these studies, the Roman Space Telescope is poised to make groundbreaking discoveries that will shape our understanding of the universe. The process of developing and confirming the telescope's capabilities has been a journey of innovation, collaboration, and perseverance. It has required scientists to push the boundaries of what is technologically possible while ensuring that the telescope meets the rigorous standards of space exploration. As the Roman Space Telescope prepares for launch, its unique capabilities represent a significant leap forward in our ability to observe and understand the cosmos. The images it captures will not only be larger than anything previously seen but will also provide new insights into the fundamental nature of the universe. This is the story of how the Roman Space Telescope was designed, tested, and confirmed as a revolutionary tool for astronomical observation, a testament to the power of human ingenuity and the enduring quest to explore the unknown. The images it captures will be so large there is not a screen in existence large enough to show them. This part of our deep dive into the Roman Space Telescope will reveal the universe in a way the JWST and Hubble cannot focus on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, humanity has looked skyward with an insatiable curiosity, driven by the desire to unravel the mysteries of the cosmos. The journey to understand our universe has been marked by milestones that transformed our perspective, from the first satellites that pierced the Earth's atmosphere to the grand observatories that now orbit our planet. Among these, the Hubble Space Telescope stands as a towering achievement, its legacy etched into the annals of astronomy. Launched in 1990, Hubble revolutionized our view of the universe by capturing images of distant galaxies, nebulae, and celestial phenomena with unprecedented clarity. Yet, even as it provided breathtaking glimpses of the cosmos, its limitations became apparent. Hubble's narrow field of view, while ideal for deep space observations, meant it could only capture a small portion of the sky at a time. This constraint became a catalyst for the next generation of space telescopes, each building on the discoveries of its predecessors to push the boundaries of what we could see. The James Webb Space Telescope, launched in 2021, represented a leap forward, offering infrared capabilities that allowed it to peer through cosmic dust and glimpse the earliest galaxies. However, even Webb's advancements were not without their own constraints. Its focus on high-resolution imaging of specific targets meant that it could not survey vast swaths of the sky in a single observation. This is where the Roman Space Telescope steps in, not as a replacement for Hubble or Webb, but as a new frontier in astronomical exploration. Its ability to capture images so large that no screen in existence can fully display them marks a paradigm shift in how we observe the universe. To understand the significance of this breakthrough, we must first trace the evolution of space-based telescopes and the discoveries that shaped their development. The story begins with the early days of space exploration, when the first satellites, like the Soviet Union's Sputnik 1 in 1957, opened the door to observing the cosmos from beyond Earth's atmosphere. These early missions laid the groundwork for more sophisticated instruments, but it was the Hubble Space Telescope that truly redefined our understanding of the universe. Launched in 1990, Hubble's primary mirror, though initially flawed, was later corrected through a servicing mission, allowing it to deliver stunning images that captivated scientists and the public alike. Its ability to capture light from distant galaxies helped confirm the universe's expansion and provided insights into the formation of stars and planets. However, Hubble's narrow field of view meant that it could only study a limited portion of the sky at any given time. This limitation became a critical challenge for astronomers seeking to map the cosmos on a larger scale. Enter the James Webb Space Telescope, a successor designed to overcome these constraints. Launched in 2021, Webb's infrared capabilities allowed it to peer into the dusty regions of space where stars and galaxies form, revealing the earliest structures in the universe. Its advanced technology enabled it to capture images of galaxies billions of light-years away, providing a window into the cosmos' infancy. Yet, despite its groundbreaking achievements, Webb's focus on high-resolution imaging of specific targets meant that it could not survey vast areas of the sky in a single observation. This limitation highlighted a gap in our ability to conduct wide-field surveys, a need that the Roman Space Telescope is poised to address. The Roman Space Telescope, named after the astronomer who first proposed the concept, is a product of decades of scientific innovation and the lessons learned from previous missions. Its development was driven by the recognition that while Hubble and Webb have provided invaluable insights, they are not without their limitations. The Roman telescope's primary instrument, the wide-field instrument, is designed to capture images of an unprecedented scale. This instrument's field of view is significantly larger than that of Hubble, allowing it to survey vast regions of the sky in a single observation. The result is a capability that defies conventional expectations: images so large that they cannot be fully displayed on any existing screen. This technological leap is not merely a matter of size but a fundamental shift in how we approach astronomical observation. By capturing such expansive data, the Roman telescope opens the door to new discoveries, from mapping the distribution of dark matter to studying the formation of galaxies on a cosmic scale. To appreciate the significance of this advancement, it is essential to understand the historical context that led to its development. The journey from the first space telescopes to the Roman Space Telescope is a testament to humanity's relentless pursuit of knowledge. Each mission has built upon the discoveries of the last, refining our tools and expanding our horizons. The Hubble Space Telescope, for instance, was a product of the Cold War-era space race, a mission that combined cutting-edge engineering with the ambition to explore the universe. Its success demonstrated the power of space-based observatories, but it also revealed the need for more versatile instruments.
The James Webb Space Telescope, in turn, represents a collaboration between nations and a commitment to advancing our understanding of the cosmos. Its infrared capabilities were a direct response to the limitations of visible light telescopes, allowing scientists to peer into the universe's most obscured regions. However, even with its remarkable achievements, Webb's narrow field of view underscored a critical need: the ability to conduct wide-field surveys that could capture the vastness of the universe in its entirety. This need became the driving force behind the development of the Roman Space Telescope. The Roman telescope's design is a culmination of decades of scientific progress, incorporating lessons learned from Hubble and Webb while introducing groundbreaking innovations. Its wide-field instrument, for example, is a technological marvel that combines advanced sensors with a unique optical design to capture images of an unprecedented scale. This instrument's ability to gather light from vast areas of the sky means that it can detect faint signals that previous telescopes could not. This capability is particularly important for studying the distribution of dark matter, a mysterious substance that makes up a significant portion of the universe's mass but remains invisible to traditional observation methods. By capturing large-scale images, the Roman telescope can map the gravitational effects of dark matter, providing insights into the structure and evolution of the cosmos. Additionally, the Roman telescope's ability to capture such expansive data opens new possibilities for studying the formation and evolution of galaxies. While Hubble and Webb have provided detailed images of individual galaxies, the Roman telescope's wide-field approach allows for the study of entire galaxy clusters and their interactions. This broader perspective is essential for understanding the large-scale processes that shape the universe, from the formation of cosmic webs to the dynamics of galaxy mergers. The historical context of the Roman Space Telescope's development is also deeply intertwined with the broader advancements in space technology and scientific collaboration. The creation of such a sophisticated instrument required the integration of cutting-edge materials, advanced computational techniques, and a global network of scientists working in unison. This collaborative effort reflects a trend in modern astronomy, where the complexity of cosmic questions demands interdisciplinary approaches and international cooperation. The Roman telescope's design, for instance, incorporates lessons from previous missions, such as the Hubble Deep Field project, which demonstrated the power of long-exposure imaging to reveal distant galaxies. However, the Roman telescope takes this concept further by capturing vast areas of the sky in a single observation, significantly reducing the time required to gather data. This efficiency is crucial for addressing the vast amount of data that modern astronomical research generates, as well as for making the most of the telescope's limited operational lifespan. The significance of the Roman Space Telescope's capabilities extends beyond its technical specifications. It represents a shift in the way we approach astronomical observation, moving from targeted studies to broader, more comprehensive surveys. This shift is essential for addressing some of the most pressing questions in astrophysics, such as the nature of dark energy, the distribution of dark matter, and the formation of the first galaxies. By capturing images so large that no screen can fully display them, the Roman telescope is not just expanding our view of the universe, it is redefining the very methods by which we explore it. The historical context of the Roman Space Telescope's development underscores the importance of building on past achievements while embracing new technologies and approaches. From the early days of space telescopes to the groundbreaking work of Hubble and Webb, each mission has contributed to our understanding of the cosmos. The Roman telescope stands at the intersection of these advancements, offering a new perspective that builds on the foundations laid by its predecessors. Its ability to capture images of unprecedented scale is a testament to the ingenuity of scientists and engineers who have worked tirelessly to push the boundaries of what is possible. As we look to the future, the Roman Space Telescope promises to unlock new mysteries and deepen our understanding of the universe. Its legacy will be defined not only by the images it captures but by the questions it helps us answer, continuing the long tradition of scientific exploration that has brought us to this moment. The Roman Space Telescope, with its unparalleled ability to capture vast swaths of the cosmos in a single sweep, promises to revolutionize our understanding of the universe. Yet, for all its power, it cannot answer every question. In fact, some of the most profound mysteries of the cosmos remain unresolved, and the telescope's data may only deepen the enigma. Take, for instance, the nature of dark energy, a force that is driving the universe's expansion at an accelerating rate.
While scientists have long suspected its existence, its true identity remains one of the greatest puzzles in modern physics.
Is it a constant, as the cosmological constant suggests, or does it evolve over time, as some theories propose?
The Roman telescope's mission to map the universe's expansion rate could provide critical clues, but even its findings might not resolve this debate. The data it collects could either support existing models or hint at something entirely new, leaving scientists to grapple with the same questions in a different form. Similarly, dark matter, another invisible force that shapes the cosmos, continues to elude direct detection.
While we know it influences galaxy formation and the distribution of cosmic structures, its composition remains a mystery.
The Roman telescope's wide field of view may allow it to peer into the early universe, where the first galaxies formed, potentially revealing how dark matter interacted with ordinary matter. But even if it does, the question of what dark matter is made of, whether it's composed of weakly interacting massive particles, axions, or something else entirely, remains unanswered.
These are not mere academic exercises, they are fundamental questions about the very fabric of the universe. The Roman telescope's observations could provide new data points, but they won't necessarily provide definitive answers.
In fact, they might complicate things further. For example, the telescope's ability to capture such massive images could reveal structures or patterns that current models don't account for. Imagine a galaxy cluster that defies our understanding of gravity or a cosmic web that suggests a different distribution of dark matter.
Such discoveries could force scientists to revise their theories, but they might also introduce new questions that were never considered. The same applies to the study of exoplanets.
While the Roman telescope's instruments could analyze the atmospheres of distant worlds in unprecedented detail, the question of whether these planets are habitable or even capable of supporting life remains contentious.
We already know that planets like Earth exist in the habitable zones of their stars, but what about the conditions on those planets? Are they truly Earth-like, or do factors like atmospheric composition, magnetic fields, or tidal forces make them inhospitable? The Roman telescope's data might shed light on these issues, but it won't eliminate the uncertainties.
For instance, a planet that appears to have an Earth-like atmosphere might still be a toxic wasteland, or a seemingly barren world might harbor life in forms we've never imagined.
These are not just scientific questions, they are philosophical ones, touching on the very definition of life and the possibility of extraterrestrial existence.
Even the telescope's role in studying the early universe raises unresolved questions. While it can peer back to the first few 100 million years after the Big Bang, the details of how the first galaxies formed and evolved remain unclear. Some theories suggest that these galaxies formed in a chaotic, clumpy manner, while others propose a more orderly process. The Roman telescope's ability to capture large-scale images could help distinguish between these models, but it might also reveal anomalies that challenge our understanding. For example, if the telescope detects a galaxy that formed earlier than expected or exhibits properties that don't fit into existing frameworks, it could force scientists to rethink the timeline of cosmic
evolution.
These findings might not provide immediate answers but could instead open new avenues of inquiry. The Roman telescope's power lies in its ability to gather vast amounts of data, but data alone is not enough to solve mysteries. It's the interpretation of that data, what scientists choose to focus on and how they frame their questions, that shapes the direction of discovery. In this sense, the telescope is both a tool and a catalyst, pushing the boundaries of what we know while also highlighting the limits of our current understanding.
Consider the debate over the Hubble constant, the rate at which the universe is expanding. Different methods of measurement have yielded conflicting results, and the Roman telescope's observations could help resolve this discrepancy. However, even if the data aligns with one model, it might not eliminate the underlying tension between theories. The Hubble constant is not just a numerical value, it's a window into the universe's past and future. A small error in its measurement could have profound implications for our understanding of dark energy, cosmic inflation, and the ultimate fate of the universe.
The Roman telescope's role in this debate is clear, but the resolution of these questions remains uncertain. Similarly, the telescope's ability to study the distribution of matter in the universe could provide insights into the cosmic web, the vast, interconnected network of filaments and voids that structure the cosmos.
Yet, the exact mechanisms that govern this web's formation are still debated.
Some scientists argue that dark matter's gravitational influence is the primary driver, while others suggest that the distribution of ordinary matter and the effects of dark energy play a more significant role. The Roman telescope's wide field of view may allow it to map these structures in greater detail, but it won't necessarily settle the debate. Instead, it might reveal new complexities that require even more sophisticated models. In all these cases, the Roman telescope is not a magic wand, it's a powerful instrument that expands our capacity to observe and analyze the universe. But the mysteries it uncovers are not the end of the story, they are the beginning of new questions. Science is a process of iteration, where each discovery leads to more questions, and the Roman telescope is no exception. Its data may challenge existing theories, inspire new hypotheses, and even reveal phenomena that were previously unimaginable. The universe, after all, is vast and complex, and no single instrument can unlock all its secrets. What the Roman telescope can do is provide a new perspective, one that allows scientists to see the cosmos in ways that were once impossible. In doing so, it ensures that the questions we ask will continue to evolve, and the mysteries we seek to solve will remain as compelling as ever. The images it captures will be so large there is not a screen in existence large enough to show them. This part of our deep dive into the Roman Space Telescope will reveal the universe in a way that JWST and Hubble cannot focus on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In this chapter, we've explored how the Roman Space Telescope is set to revolutionize our view of the cosmos in ways that the James Webb Space Telescope and Hubble simply cannot. At the heart of this breakthrough lies a simple yet staggering truth: the images it captures will be so vast, so detailed, that there is no screen in existence, no massive display, no cutting-edge monitor large enough to show them all at once. This isn't just about resolution or clarity, it's about scale. The Roman telescope's field of view is designed to sweep across the sky in a way that feels almost cinematic. Imagine a telescope that can capture entire galaxies in a single shot, or track the subtle dance of dark energy across the universe's fabric. This is the power of its design, a leap forward that redefines what we mean by seeing the universe. But why does this matter? Because the Roman telescope isn't just another instrument in the sky. It's built to answer questions that have long eluded astronomers. For decades, scientists have grappled with the mystery of dark energy, the invisible force accelerating the universe's expansion. While Hubble and JWST have provided glimpses into this enigma, the Roman telescope's unique capabilities will allow it to measure cosmic distances with unprecedented precision. By studying the subtle shifts in light from distant supernovae, it will help us map the universe's accelerating expansion in ways that were previously impossible. This isn't just about data, it's about unlocking the very rules that govern the cosmos. Then there's the question of exoplanets. The Roman telescope will peer into the faint glimmers of worlds beyond our solar system, searching for signs of habitability. Unlike Hubble, which has spent decades studying these distant planets, Roman's wide field of view will allow it to survey thousands of stars in a single observation. This means it can detect the faintest signals of potential life-supporting atmospheres, or even the faintest whispers of planets orbiting stars in the far reaches of the galaxy. It's a tool that bridges the gap between the grand scale of the universe and the intimate details of alien worlds. And yet, the most striking takeaway is this: the Roman telescope isn't just about what it can see, it's about how it changes the way we see. The images it produces will be so large, so immersive, that they challenge our understanding of what a space telescope can do. They will force us to rethink the limits of our technology, the scope of our curiosity, and the stories we tell about the universe. This is a telescope that doesn't just observe the cosmos, it invites us to step into it, to experience it as a vast, interconnected web of light and mystery. So what does this mean for us? For the scientists who chase the edges of knowledge, for the engineers who build the tools to reach them, and for every curious mind who looks up at the stars. The Roman telescope is a testament to human ingenuity, a reminder that the universe is still full of secrets waiting to be uncovered. And as we stand on the brink of this new era of discovery, one thing is clear: the cosmos is about to reveal itself in ways we've only begun to imagine. If you've enjoyed this deep dive, consider subscribing to FactVerse for daily explorations of the universe's biggest questions. Whether you're a lifelong stargazer or a first-time viewer, there's always more to learn. And if you have your own theories, questions, or ideas about what the Roman telescope might uncover, we want to hear from you.
Drop a comment below and join the conversation.
Because the universe is vast, but our curiosity is limitless, and together, we're just beginning to explore it.